The topic of this video is long multiplication. I'd like to show you a nice systematic way of doing the calculation. It's nice because it's easy to do. It's nice because it's easy to check, which is important. You should always check the work. In particular, you should design the work from the very beginning to make it easy to check. The method's also nice because it's easy to understand in terms of things you already know. Nice simple things like place value and the distributive law. This is the second of two videos. In a previous video, we discussed the background and the principles involved and did some simple examples. In this video, we're going to talk about the recipe in all generality so that you can multiply anything by anything. Let's do an example of long multiplication that is big enough to illustrate almost all of the features you need to know about the method. Let's multiply 4,567 by 321. As always, we're going to use the methods we discussed in the previous video. We're going to pick both these numbers apart into individual digits and proceed digit by digit. We start with this number here. It's the low order digit of the second factor. And 1 times 7 gives us a 7, which goes here, lined up under the 1. 1 times 6 gives us 6, which is just shifted over one place. 1 times 5 gives 5, which goes here. 1 times 4 is 4, which goes here. We now proceed to the second digit of the second factor, which is 2. That gives us a 14, which we write here. And that's lined up with the 2. We now go to the 2 times 6, which is 12. We'd like to write that here, just shift it over one place. We'd like to write something like this, but we can't because there's somebody already there. We can, however, move down a line and write it here. Same thing goes for 2 times 5. That's a 10. It's going to be shifted over one place. We write that there. And last but not least, 2 times 4 is 8. And that has to go here, shifted over one place. So within each group here, this is a group we get from multiplying by 20. Within this group, everybody is shifted over one place from the thing above it. And you can see that pattern, things being shifted over one by one, according to this nice diagonal line. That's how you keep things properly lined up in columns. So you absolutely could write it this way. This is entirely correct. It's not, however, as compact as it could be. And also it isn't finished. We haven't taken care of the last digit here. On this slide, we're going to do the exact same problem as last time with a couple of refinements. So here's the thing we did last time. For one thing, it's unfinished, so you have to finish it. And second of all, it's not as compact as it could be. So let's see if we can do this one more time. The multiply by ones, I've already done here. Let's move on to the multiply by 20. 2 times 7 is 14, which goes here. Then 2 times 6 is 12, and that goes here, shifted over one place relative to the 14. Next comes 2 times 5, which is a 10, and we could write that down here like we did last time, but we don't have to. We can write that up here because there's room for it. That's a little more compact. Last but not least, 2 times 4 is 8, which we write here. Now we move on to the 3's digit. 3 times 7 is 21, and that goes here, lined up under the 3. Next is 3 times 6, which is 18, which has to be shifted over one. Let's put that there. Then we have 3 times 5 is 15, which goes here. And last but not least, 3 times 4 is 12, which there's room for here. And that's it. That's all the short multiplication. All we got to do now is add them up. So the 7 comes down here. 6 plus 4 is 10. Carry the 1. 6, 7, 9, 10. Carry the 1. 5, 6, 8, 16. Carry the 1 makes 2, 10, 16. Carry the 1 makes 4. And that's our answer. So there's a couple points to make about this. That first of all, note that we did all of the short multiplying first, multiply, 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 and then we did all of the adding. And that's important that's part of what makes this checkable, because you know exactly where each of these guys came from. That this is the by ones row here. This group here is the by 20s, and this group here is the by 300 group. And within each group, you know exactly where everybody came from. That this 14 came from this 7, and the 12 came from the next digit, and so on. First, second, third, fourth. Nice little systematic pattern here. And in this group here, first digit, second digit, third digit, fourth digit. So we know exactly where all these came from. So things you can repeat the multiplication. That you can redo 7 times 1 gives you this. 7 times 2 is going to give you this 14. 3 times 6 is going to be down here. It's going to give you this 18. You can recheck all of those. This works even if you don't have colored ink. If you only got one color ink, you can get by with underlining the guys. So if we underline this 6, he shows up here, and he shows up again here, and he shows up again here. So once again, you can keep track of where these guys came from. And if you want to keep track of the 5, you can double underline him. He shows up here, and he shows up again here, and he shows up again here. So you can keep track of where everybody came from, where everybody wound up. You can redo it, redo the multiplications. If you mix the multiplying and the adding with the carrying, blah, 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 you'd have this bunch of digits. You'd have no way of debugging it, no way of auditing where they came from. You can also check the addition here. Just do it twice. When I do it the second time, I do it in the reverse order up from the bottom. Well, 7 just makes 7. 4 plus 6 makes 10. Carry the 1. Up from the bottom, we get 2, 4, 5, 10. Gives me a 0 here. Carry the 1, make 9, 11, 12, 16. Carry the 1. 2, 7, 15, 16. Carry the 1, and so on. So this way of laying things out, first do the short multiplying, then do all the adding. It allows you to keep track of where things came from, allows you to check the multiplies, allows you to check the addition. I'd like to say a few words about how we keep things properly lined up in columns. It pays to think about these things in groups. This is the by ones group, it comes from the first digit of the lower factor. This is the by 20 group, comes from the second digit of the lower factor. And this is the by 300 group that comes from the third digit of the lower factor. The first thing to notice is that each group is shifted one place to the left relative to the group before it. That guy is shifted over one place, and that guy is shifted over one place. That's because the groups inherit place value from the lower factor. That the start of the group is lined up with the digit that produced that group. The second thing to notice is that within each group, each of the products we get from short multiplication is shifted over one place. So this 7 is lined up here. The next product within the group is shifted over one place. The next product is shifted over. The next product is shifted over. Within this more complicated group here, this is the first product. This is the second product shifted over one place relative to the previous product in the group. Shifted over another. Shifted over another. So those are the rules. Within the rule I just gave you within the group comes from the fact that each of these products inherits place value from the upper factor. So the start of the group inherits place value from the lower factor, and within each group, each product inherits some place value from the upper factor. So it's all perfectly logical. Let's do one more example here. It illustrates an idea that didn't show up in the previous example, something you need to do sometimes to keep yourself out of trouble. Same method, we'll pick this apart into digits and start multiplying. 3 times 3 is 9, which goes here. However, I'm anticipating trouble, so I'm going to write that as 0, 9. Moving on to the next digit. 3 times 2 is 6, which goes here, but I'm anticipating trouble, so I'm going to write that as a 0, 6. You'll see why in a minute. 3 times 8 is 24, and that goes here, and that's taken up 2 digits, which is which is the whole idea here. 3 times 1 is 3. I'm going to write that as 2 digits. I'm going to write that as 0, 3, even though we don't exactly have to. Now we move on to the 2's digit here. 2 times 3 is 6. That lines up under the 2. So write that as a 0, 6. 2 times 2 is 4. That's got to be shifted over one more. So let's write this as 0, 4. 2 times 8 is 16. And there's room for that here. And 2 times 1 is 2. So I'm going to write this as a 0, 2. Now, most of these numbers here, I could have written them as 1 digit, but I wrote each of them as 2 digits just so we get this nice alternating pattern. 2 digits here, 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 shifted over 1 each time. Just so it falls into a nice pattern, just so it falls into a nice rhythm, keeps you out of trouble. And now all we need to do is the addition problem. So this 9 comes down here. 6 and 6 makes 12. Carry the 1. We get 5, 9. Okay, 5 makes 11. Carry the 1. This gives us a 4. So that's probably the right answer. So the rule here is simple. Use 2 digits for each product unless you're sure you don't need to. Just so things fall into a nice systematic pattern. Systematic is good. Let's summarize what we've discussed. Graph paper helps, especially at first. The best thing is a lab book. Such things are cheap and readily available from office supply stores. On the other hand, once you understand the importance of keeping things lined up in columns, you can discipline yourself to keep things lined up, and then you can do fine without graph paper. The most important idea is that long division can be understood in terms of the distributive law and the axioms of the numeral system, really basic stuff that you already know about. There's a smart method for organizing the calculation. Proceed digit by digit. First do all the short multiplying, then do all the adding. Use columns to keep track of the place value. And that's pretty much all there is to it. Using this method, you can multiply anything by anything.